Hello friends, in this video I'd like to solve the following problem from the William Lowell Putnam Mathematical Competition 1985, problem B5, so from the higher series of problems, quite difficult, you shall see in a moment. So we wish to evaluate the following improper integral from 0 to plus infinity of t to the power minus 1/2 times e to the power minus 1985 times t plus 1 over t dt. So a lot of things are going on here. Hints. This problem is difficult, but my hints. First of all, there is a well-known result. I believe it's called Gauss integral, which says that the integral from minus infinity to plus infinity of e to the power minus x squared dx equals the square root of pi. So the basic idea is to somehow connect our integral given in our problem to this integral. Second hint, you can make the following substitution: t equals x squared. Then you can try changing variable to x from x to 1 over x. You shall see in a moment. And eventually, if everything goes right, we will get, or you will get, something like the integral over some interval of g prime of x, derivative of g, times e to the power g of x dx, which can be dealt with quite easily after all that. So try your best and see you in a minute. Okay, so I hope that you tried your best. And now, first of all, as I suggested, let's take our integral from 0 to plus infinity, t to the power minus 1/2, e to the power minus 1985, t plus 1 over t dt. First of all, we make the following substitution: t equals x squared. It's legal because our interval of integration is from 0 to plus infinity, and we know that function x squared is bijection on this interval. Dt becomes 2x dx. Okay, and bounds of integration remain exactly the same. And we get, after our substitution, we get the integral from 0 to plus infinity of t is x squared, so x squared to the power minus 1/2 is x to the power minus 1, e to the power minus 1985, x squared plus 1 over x squared, and dt is 2x dx. Okay. After simplification, we can put 2 in front of our integral, and with x to the power minus 1 and this x, they cancel each other out. And we get integral from 0 to plus infinity of e to the power minus 1985 x squared plus 1 over x squared dx. Nice. Okay, but now let's do the following. So let's call this integral, our integral, let's call it I. Let's call it I. And now it's I. And now let's observe that we can make the following change of variables. Instead of, let x be 1 over y. Okay, then dx becomes dy over y squared minus dy over y squared. And our bounds of integration, since x was from 0 to plus infinity, y becomes from plus infinity to 0, because 1 over 0 squared is plus infinity, 1 over infinity is 0. Okay, so our integral becomes 2 times integral from plus infinity to 0 e to the power minus 1985 1 over y squared plus y squared minus dy over y squared. Okay, and now classic trick, since we have minus here, we can change the bounds of integration, and we have twice the integral from 0 to plus infinity. And one more thing, since we are dealing with a definite integral, the name of a variable doesn't really matter. We can change back from y to x, and we'll get 1 over x squared e to the power minus 1985 x squared plus 1 over x squared dx. Very nice. Now, what now? Okay, now we have expressed our integral in two different ways. This was one way to express our integral, and the second way was here. Now, the basic idea is to add these two integrals, these two equations together. And we can deduce the following. 2 times I is 2 times the integral from 0 to plus infinity e to the power minus 1985 x plus 1 over x squared dx plus twice the integral from 0 to plus infinity 1 over x squared e to the power minus 1985 x squared plus 1 over x squared dx. And now we can divide both sides by 2, and we can combine these two integrals in one integral. So we know, maybe let's write it in green, our integral equals the following. Integral from 0 to infinity. And now let's look. This part, e to this power, is the same as this part. So we have 1 plus 1 over x squared e to the power minus 1985 x squared plus 1 over x squared dx. Okay. Now, the crucial part. I suggested that we should get some integral of the form g prime of x e to the power g of x or something like that. Now, let's look at this part. This part is a derivative, the derivative of some function, namely, it's derivative of the function x minus 1 over x. So the basic idea is to there should be square here, probably doesn't matter, and minus doesn't matter. The basic idea is to express this part as x minus 1 over x plus some terms. So we can do that in the following way. So we have our integral from 0 to plus infinity of 1 plus 1 over x squared e to the minus 1985 And now this parenthesis can be written as x minus 1 over x squared plus 2 dx. Because x squared, 1 over x squared, minus 2 plus 2 is exactly the same as above. Now, let's do the following. We can express that as integral from 0 to infinity, 1 plus 1 over x squared, e to the power minus 1985 x minus 1 over x squared times e to the power minus 2 times 1985 dx. Okay, and now let's look. This part is a constant, so we can put our constant in front of our integral. And now we have 1 over x squared e to the power, and moreover, one more thing maybe. I will write minus the square root of 1985 x minus 1 over x, everything squared dx. Perfect. And now I will make my final substitution. So finally, after all of that, I will make the following substitution. U, let's say, u equals the square root of 1985 times x minus 1 over x. And now du becomes the square root of 1985, 1 plus 1 over x squared dx. And what happens to our bounds of integration? Well, since x was from 0 to plus infinity, when x goes to 0, 1 over x goes to plus infinity, but we have a minus in front. So we have u goes from minus infinity. And when x goes to plus infinity, this expression also goes to plus infinity. Moreover, I will leave you as an easy exercise. No, not. It's obvious. This function is bijective because it's increasing. Why is it increasing? Because derivative is positive. So it's bijection. U is a bijection between 0 plus infinity to real numbers. It's bijection. Okay, so this substitution is perfectly legal. Okay, and now I need another page, so wait a minute. Okay. Let's look. And now, okay. One more thing, maybe. I will a bit artificially write in our previous integral. I will divide here by the square root of, no, I will, in fact, multiply by the square root, and I will here divide by the same square root. And now, what happens? Now, we have the following. Our integral is e to the power 2 times 1985 over the square root of 1985. Integral from minus infinity to plus infinity. And this and this is exactly du. And this part becomes e to the power minus u squared. The famous Gauss integral. And by the well-known result, this integral is in fact equal to the square root of pi. I will not prove it here because the proof is quite lengthy. You can find it in practically every standard mathematical analysis calculus textbook, or on Wikipedia, or on YouTube for that matter. So finally, we have, now comes the hard part, which I am not prepared for. 2 times 1985. Let's multiply these two numbers. 2 times 1985 is 3970. So our final result is e to the power minus 3970 square root of pi over 1985. Believe it or not, according to Wolfram Alpha, for example, or every other algebra system, this is the correct result. So our integral from 0 to plus infinity, e to the power minus 1/2, e to the power minus 1985 t plus 1 over t dt equals e to the power minus 3970 pi square root of pi over 1985. And that concludes our video. Quite a challenge. So thank you for watching. I hope that you were entertained, that you learned something new, that you, I don't know, that you liked my work. So see you next time. Goodbye.